Hello, everybody. So, for today's video, this is going to be the first part of a series that I like to call Study SESH. So, in this series, I'm just going to be studying any topic that I choose. Okay, and one topic that really picked one topic that really piqued my interest is what we call the Navier-Stokes equations, and you probably have already heard of this. Navier-Stokes equation is just a set of equations. Okay, it's just one set of equations for the many set of equations that are a part of this sort of cash prize competition to see who can win, to see who can get the correct answer for these equations, and you can get $1 million from it, I believe. But I don't have any prior knowledge about the Navier-Stokes equation. I'm really just winging it out and see what happens. But you know, I'm interested to learn. You could probably say that I'm just reverse engineering this thing by starting from the very most complex stuff. You know, so I got this little PDF from Cambridge. So source will be from Cambridge. It'll be right here in cambridge.org. You can check it for yourself as well. It's a student's guide to Navier-Stokes equations. Okay. So this is the first page of the alternative approach for the vector gradient. Student's guide to the Navier-Stokes equations, supplement on an alternative calculation for the velocity gradient and Cartesian coordinates. So this is basically going to be velocities in Cartesian plane. Okay. So as you already may know from physics, a vector is basically just magnitude plus direction. Okay. Magnitude plus direction, and it entails little arrows. Vectors are basically just little arrows. We can just make that the analogy for vectors. Okay, so we can further understand what this entails. So it says here, let's write out the velocity gradient in the following manner. But first, it helps to understand what all these signs mean first, so we can have a good idea of what we're really going to do here. So I asked ChatGPT earlier. It says here, what you're looking at is the expansion of the gradient operator. I don't really know what a gradient operator. What is a gradient operator? Okay. Gradient operator, denoted as this upside down triangle, or del/nabla, is a multivariable calculus tool that transforms a scalar field into a vector field. So, from my own understanding, I believe scalar. When you talk about scalar, okay, when you refer to scalar, something scalar, it basically just denotes that. If you have heard in linear algebra, okay, like the very basics of linear algebra, anything scalar is just a magnitude of something. So you can say that the speed of a car is scalar. Okay, the speed of a car is scalar, like the kilometers per hour. That's a scalar. Okay, and the vector is kind of like you have magnitude plus direction. So with a scalar, if a scalar of the car, if car speed is kilometers per hour, it's probably the vector field would probably be probably be something like kilometers kilometers per hour, and then it says that you're heading northeast, for example. Like, but that's my understanding of scalar and vectors. But let's dive deeper into this scalar, what they call a scalar field and a vector field. It says here the gradient operator is a multivariable calculus tool transforms a scalar field into a vector field. Okay, so let's first search of a scalar field, I guess, first. So just to get a little brief understanding of what a scalar field is. Okay, because most of what we're doing in this video right now is just a little bit of guesswork and some foundational knowledge. I don't really know anything about the Navier-Stokes equation, to be honest with you. So we're learning it together. That's the point of this video. Sorry, that was very redundant. Okay, so it says here, the scalar field in mathematics. Wait, let me see. Just click. Okay, in mathematics and physics, a scalar field is a function associating a single number to each point in a region of space. Okay, so we're basically just so we're using a sort of a Cartesian plane right here, a scalar field. So it says that it is a function. So if you I could assume that the function functions like functions in order to f of x. Yeah, associating a single number to each point in a region of space. Okay. Scalar may either be pure mathematical number or a scalar physical quantity with units. In a physical context, scalar fields are required to be independent of the choice of reference plane. That is, any two observers using the same units will agree on the value of the scalar field at the same absolute point in space or space-time, regardless of their respective points of origin. Examples used in physics include the temperature distribution. Why do I keep clicking stuff? Examples used in physics include the temperature distribution throughout space, the pressure distribution in field, pressure distribution in fluid, and spin zero quantum fields such as the Higgs field. These fields are the subject of scalar field theory. So what I understand that basically just says that, okay, let's pull out the good old Microsoft whiteboard. Let's just pull out the good old Microsoft whiteboard, okay? So let me just pause for a second. Just for you, for giving me a chance. I'll be your angel. All right, we're back. I just had to log in my Microsoft account in the Microsoft Library thingy here. So what my understanding is of scalar field. So they basically is a representation of something, just multiple points in a single field. Okay, just multiple points in a single space. So you can understand, if we could extract one of the examples of the scalar fields, we can see that one of the examples of scalar fields are temperature distribution throughout space. So if you could imagine space, okay, you can imagine space right here. Sorry, that was a very bad. You can just imagine this black little lines, black doodles in space, okay? So you could probably just copy. I could probably just copy that. I'll just copy that. That'll make our job more easier. Like, okay, so we can see right here. We can just imagine these little gradients right here. These little color gradients are what entail what space temperature distributions look like. So we can see if you can see right here. We can just assume that these little the lighter ones, the blue ones, represent cooler temperatures, okay? And then these are hotter temperatures, the red ones, okay, the red and yellow ones and the green ones, okay. So based on that information, we could deductively conclude that a scalar field should involve various points, okay? Just various points, let's say point A, point B, you know, yeah, yeah. It's various points in any space, okay? That basically describes something, okay? So now let's check out what a vector field is. And how does it relate to scalar fields? Because this little this student guide, okay, this the Navier-Stokes equations, a supplemental and alternative calculation for velocity gradient and Cartesian coordinates. So it's a very specific. They're to be calculating a velocity gradient, like a velocity gradient, okay, the Cartesian coordinates. So what? So a vector. When we talk about velocity, we're always going to come back to vectors. Okay. So what is a vector field? Let's see what a vector field is first. Okay. So vector field. Vector fields are an important tool for describing many physical concepts such as gravitation and electromagnetism, which affect the behavior of objects over a large region of a plane or of space. They are also useful for dealing with large-scale behaviors such as atmospheric storms or deep-sea ocean currents. In this section, we examine the basic. Okay. Examples of vector fields. How can we model the gravitational force exerted by multiple astronomical objects? How can we model the velocity of part? Wow. Okay. Let's just come to this one little example. Okay. Let's go to this one little example. You can see it right here. This is probably what we call the velocity, no, that's wrong. This is what we call a vector field. So you can imagine right here, okay, let's say that you have, this is just one of the multiple examples that you can use in order to really visualize what a vector field is. But the example that really sticks to my head is, I can imagine a little hole, okay? I can imagine a hole right here. And around the hole, okay? Around the hole, there's basically just water flowing, okay? It's basically just water flowing around the hole. And naturally, through gravity, you know, let's just say that the hole is very steep, it's very deep, very deep, okay? And this is the ground. We can just imagine this little hole as sort of a pothole, you know, sort of a pothole, okay, in the road. And let's suppose that it's not very good weather conditions and it's really raining. So obviously, through gravitation, you know, through gravity, the water currents are also going to come inside the hole. And if we try to look at the hole from from on top of it, okay, just from on top of the hole, okay, like let's say this is the hole, okay, this is there is water getting in the pothole, okay? And this is where velocity. I keep mixing it two stuff up, okay. So this is where the vector field would probably make sense because, okay, so we can just imagine this table, okay, Cartesian plane, and a vector field is, in my understanding, is probably just a lot of vectors, just a lot of vectors, okay, just, and they're navigating towards this hole, this center right here. And this is going to be negative, I believe, but I'm going to have to clarify for myself what the concept of this is, because I saw it in a video, I believe, I already saw this in a video. Let me just search what video it is. I know I saw this in a video. There's an explanation of what I'm talking about. And okay, here's the video by V Cubing X. Thank you very much for this video. It's very informative. Okay, so all credits to him. I'm just going to play a little tidbit of the video because I don't want to get copyrighted. Okay. Okay, so here's what he's talking about. It's rolling fluid, pressable, thermal. Hey, here we go. Okay, here we go. So, divergence. Degree moving away from the origin. This indicates positive divergence. Similar. So, we can just write that out. So, if we can look at an analogy earlier that or the example that I made earlier, it's a pothole, and the water is coming inside, so that means that it has a negative divergence. So we could probably say that the sort of denotation of it would look like this. So div f. So I believe it's yeah, like that. This vector field seems to have vectors that flow into the origin. This indicates negative divergence. Numerically, we write the divergence as a dot product between the gradient vector and its vector field. Let me just screenshot this. And, I want to ask ChatGPT what this denotes to. This is mean. The symbol in your image means the divergence of the vector field. What is F? F is a vector field. Okay, it's actually a vector field. I thought it was some kind of variant of the F from mass times acceleration equals force. I thought it was this. I believe. Oh yeah, this the Newton's Scalar motion. I thought it was that. I thought it was force. It assigns the vectors at every point in space, like a velocity field. Okay, so just as we said, it assigns a vector in every single field, or this Cartesian plane field. Okay, like a velocity vector for flowing water. Okay, or force field. What does divergence mean? Divergence measures how much the vectors are spreading out or converging at one point. Imagine air flowing through space. Positive divergence. Air is flowing outward from that point or a source. Negative divergence. Air is flowing inward toward the point. Sink. Okay, so we're just going through one of the examples of negative divergence in vector fields. Okay. Very sorry for the abrupt interruption. So let's go back to the equation. Now that we've got a better kind of idea what a scalar field and a vector field is, it packages all. Let's go back to the gradient operator. It packages all partial derivatives of a function into a vector. So we're dealing with partial derivatives here. I've already gone through that. I haven't gone through that yet. It's calculus 3. The partial derivative measures how a function with multiple variable changes when one variable is altered. One variable is altered, one variable is constant. Now that we have the brief discussion, rate qualitative function derivative represents the rate of change of functions x changes. This is an important question. completion derivatives. We're not going to want to lose it with functions with more than one variable. The problem with functions with more than one variable is that there's more than one variable. In other words, what do we do if we only want one variable to change, or want more than one of them to change? In fact, if we're going to allow more than one of the variables to change, there are then going to be an infinite amount of ways for it to change. For instance, one variable could be changing faster than the other variables. The function. Notice as well that it will be completely possible for the function to be changing differently depending on how we allow one or more of the variables to change. Okay, so what I understand derivatives to be, what I understand partial derivatives to be is they're basically just derivatives, okay? If we could take the concept of derivatives in calculus, we're basically just dealing with one variable, okay? So we're just dealing with the change of one variable. Now, partial derivatives are kind of like the extended version that, the upgraded version of derivatives. So instead of just one variable, we're trying to track the change in multiple variables in a single function. Okay. So it says here we will need to develop ways and notations for dealing with all of these cases. In this section, we are going to concentrate exclusively on on only changing one of the variables at a time, while the remaining variables are held fixed. We will deal with allowing multiple variables to change in the later section. If we're going to, let's start with a function. Okay, let's just head straight to the example. This guy's talking a little bit too much. Okay, no offense though. Okay, so since this is notes down, let's start with a function. Okay, let's try to go through the foundations of the vector. Let's go through the foundations of this concept first, before we get to the juicy stuff. So, okay, let's start with a function. Let's start with a function of x and y. Okay, so 2x squared times y cubed. And let's determine the rate at which the function is changing at a point, a or b. If you hold y fixed and allow x to vary, and if you hold x fixed and allow y to vary, so we'll start by looking at the case of holding y fixed and allowing x to vary. So if you are interested in the rate of change with function of a, b, and are holding y fixed, this means we are going to always have y equals b. If we didn't have this, then eventually y would have to change in order to get to the point. Doing this will give us a function of only x's, and we can find our new function as follows. Wait, is this what signifies a partial derivative, or this is a function of a single variable? So we're basically just making x a fixed number. Okay, I don't know. We're basically having x vary first, and y be a fixed number. So y equals b. So we're just gonna have b here. It's a function of a single variable. At this point, all that we are asking is to determine the rate of change g of x at x equals a. In other words, we want to compute g prime a, and since this is a function of a single variable, we already know how to do that. Here's rate of change at function a comma b. If you hold y fixed and allow x to vary. Okay, so this is the function. It says that this is the rate of change function of a comma b. If you hold y fixed, g prime a equals 4ab cubed, 4 times a times X times A times B. Oh, no, no, no. 4 times AB times 4 times AB cubed, okay? We will call G prime A the partial derivative. Okay, so I was right. I was right earlier. This word he says are these signs for the partial derivative of f of x and y with respect to x. And a comma b will denote it the following way. Okay, okay. It's basically just changing the variables. We can see right here that he changed y to b and then he changed x to a. So it's basically just x and y. It's basically just x and y. So we call G prime a. Now let's do it the other way. Okay. Let's ask the question. So we have the first example here. Example 1, let f(xy) equals x squared plus 3xy plus y squared. Okay, okay. So this basically is partial derivative sign. How do we say this? How do we say this? To make it easier. Partial derivative. Treat y as a constant. So the partial derivative of a function so basically just so this is basically just derivatives, okay? Obviously. So you differentiate each term x squared to 2x. X squared to 2x. 3xy. Xy is a constant. Y squared equals 0. Y squared is 0. Now keep x constant. So anything that is considered a constant will naturally equate to 0. That's my key takeaway in this. It's basically just derivatives, but there are multiple things involved. So it's just a sign of. This is just a sign of partial derivatives. We can just completely ignore that and just go to variables. Now keep x constant over here. We're going to keep x constant here. X squared is equal to 0, 3xy. 3xy is equal to 3x, and y squared is equal to 2y. So they're using the power rule for this, for the y squared. And I'm not really sure what they're using here, but because I've got 3x and 3y. Okay. So whatever term for the second part, these partial derivatives are the differentiated version of it. Whatever is constant will remain. Okay. Whatever a variable you made constant will remain in the second part of this. We're just going to use the power rule for everything. So partial derivative of x, y, differentiate only with respect to them. Okay, so I got an idea. I have a now I have a sort of a clue. Now I have a sort of a clue on how all of it works. Okay, but I'm going to be right back. So let's get back to the topic right here. I'm going to try to solve my own partial derivatives equation first. So I'm going to extract this example from the organic chemistry tutor. You could also check his channel out. He's basically the GOAT when it comes to all math, all existing math. Not sure why this guy hasn't won a Fields medal already. Okay, so let's get the example that he has right here. Let's say f of x y equals 7x squared. Okay, 7x squared minus x cubed y4 plus y4. Then I'm just going to check if my answer is correct along the way. So we have 7x squared minus x cubed times y4 plus times y raised to 4 power plus 5x raised to 4 times y cubed. Okay. And now we're going to solve for the partial derivative of a function with respect to x. So we are going to make y, the variable y, constant first before we get the answer. So you got to write the f with respect to x equals. Okay, so now let's if we learned anything from my calculus video that I created a couple days ago, it's very recent, but if we learned anything from that, it's the power rule. Okay, it's the power rule, the never changing power rule. It's very important in calculus, because if you don't know what the power rule is in calculus, you're never going to survive this subject. I'm just going to be very honest with you. If you don't know the foundational, the most basic stuff in calculus, you can't assume that you can solve these as easily as you think. So we're just going to proceed with answering this question first. So now we have x, right? We have x. What is the power rule of x squared? That's basically that. So as we have already learned, it is x raised to n equals n times x raised to n minus 1. Okay. So now we have to get the power rule first of this. Power rule of x squared. So now we have 7 times 2x minus, what is the power rule of x cubed? It's basically just 3x squared, and then we just copy the y variables, because we're treating y as a constant here. Okay, so we just copy the y variables plus 5. Hold on, 5 for x cubed, 4x cubed times y cubed. So now we just have to solve this equation. So 7 times 2x is basically 14x. 14x minus 3x squared. Hold on. 3x squared. Oh, sorry about that. Okay, so 3x squared, y raised to 4 power plus 5. 5 times 4 x squared, x cubed, 4 times 5 times 4 x cubed is basically just 20x cubed. 20x cubed then y cubed. Okay. So I believe this is going to be the answer for f of x and y with respect to x. This is the partial derivative for this equation. Okay, I'm just going to recheck if I'm correct in my assumption. So we're just going to the good old organic chemistry tutor. And I'm correct. The correct answer is this. Okay, I'm right. So let's just check that. You know. Okay. So now we're going to solve for a function of partial derivative of y respect to y. Okay. So fy equals. We're going to, as you may have already realized in calculus, whenever you have a constant number, okay, whenever you have a constant number, you always equate that to 0. You always turn the constant to 0. Okay? So now we have, since this is a constant of all these numbers, it's going to equate to 0. Okay? So we just treat the x variables as constants. Okay, you just treat the x variables as constants, and we use the power rule again. So I believe it's going to be 4y cubed. Cube plus, it's probably going to be this way, but I'm not sure yet, so let me just write out the differentiation. Y cubed plus 20x cubed, we got y 3y then squared. I think it's going to be the answer. And it turns out I'm actually wrong at this. Mistakenly, I used the partial derivative of the function of x, the variable x, instead of the actual complete equation right here. So I'm just going to circle back and calculate it again. Okay. So we have a constant here, x cubed. We got x cubed. Then 4y cubed plus, yeah, 5x power 4 with 3y squared. I believe that is the correct answer. I believe that is the correct answer. Yes. Okay. So we're just going to see if my answer is correct. Yes, it is correct. Okay. So in order to simplify this, we just simply have to distribute the x variables here with the y variables inside of parentheses. So let's start off with that. Okay. So we're just going to negate a 0 over here. It really doesn't matter if 0 is there or not. 0 is useless. Okay, that's a very good way to put it. But we got 4x, 4. We got 4. Basically, just 4. Okay, 4x cubed. 4. Why is my look? Let's say 4x cubed, then y cubed. Oh God. Sorry about that. We got, okay. So 5 times 3 is 15x 4. And then we got 4y squared. It's going to be the answer for this. I believe it is. I believe my answer is correct. Okay, I'm right. Why did I doubt my answer? I'm actually right. Right. We just forgot one single point that is wrong. It's the negative sign here. Because as you have already seen in the x cubed, there's a negative sign right here, so we're just going to copy that. Okay, I don't know why I negated that subtraction sign. I was too busy trying to poke fun at the 0 right here. It's this egg looking. It looks like an egg. Okay, so this is the correct answer. And let's go with another partial differential equation before we move on to gradient operators. I believe that's gradient operators. Okay, let's just do another partial derivative example that we can move on.
Minus 4 to the 7th plus 4 by the 8th. Find the first partial derivative with respect to x and with respect to y.
Okay, so we're just going to copy this example here from the organic chemistry tutor. Okay, so we have z equals 3x squared y to the power 4 minus 5x to the power 7. Just 5x to the power 7. Just going to find function in respect to x and y. Again, here for y to the power of 8. Right. Now let's go and first we find it. First we isolate y. Okay. Now we got 3x cubed, 2x, y 4 minus 5, 7, 6. Oh, that's wrong. Wait, let me just find the. It's actually wrong. So we got 5x. Oh, no. Oh my god, why is my Control Z not working? I don't know why, but my Control Z is not working right now. This is going to be very, very hard to do. Let me just refresh the site. Okay, so we're back. Let me just see if it works here. Yeah, it's working. Okay, so 5, and then we have times 7x to the power of 6, and then plus 4 times 8 y. 4 times 8 y. Oh, never mind. I forgot that we are supposed to keep the y variables constant. Okay. So yeah, let's just go from here. We got 6x y raised to 4 minus that's 5. 7 is maybe 35 x 4 shape, so 4y. It's going to be the answer for this partial derivative with respect to x. Now let's isolate the x, okay? Let's isolate the x again. You know, I kind of feel for these numbers, bro. They're all so isolated. That kind of deep, bruh. Okay, so let's go back. Let me just see if it's still recording. Yeah, it's still recording. Okay, so let's isolate y in this function right here. Okay. Oh, look, I mean, isolate x. Just a correction. We gotta isolate x. So, yeah, 3x squared. And 4y cubed minus 5. I believe you're just gonna go from there. Let me just go from there and see if my final answer is correct. Mi carito.
Now, say this DC. This is the answer. That's the partial derivative with respect.
Oh, oh my God! Sorry about that. I forgot. I was supposed to multiply this. We got 8 times 4 is 32 by 7, I think. So we're supposed to multiply that. Let me see right here. Okay, so I got something wrong. For some reason, 5xy is supposed to be a 0. Okay, it's supposed to be a 0. But I don't know exactly why 5x7 is supposed to be a 0 here. But the pattern that I recognized is that whatever is the negative here will be considered a constant, I believe. And it's going to be a 0, but we're going to just completely negate that in the final answer. See? Completely negate that in the final answer. And so we just have this. We would just have this. Yeah. We would just have this. This will be the correct answer. Okay. So now we've carefully solved those partial derivative equations. Let's go back to gradient operators, okay? Let's try to solve one of these. Packages of partial derivatives of function into a vector, indicating the direction of the steepest increase of scalar quantity. Steepest increase of the scalar quantity, the maximum rate of that increase. So it says here they FOIL the derivatives. The del operation. What is a del operation? Is this gradient operator? I believe it is. Let's try to disregard this for now because this is really in-depth, sort of advanced equation. But I want to solve something related to Navier-Stokes equation. So let's just Let's just search for example problems and then we can go from there.
Okay, I thought I'd record the z and y components of the fluid velocity are zero. So you're told that v and w are zero. The upper wall here is fixed, it's stationary. But the flow is driven by the motion of the problem states, consider steady laminar flow of viscous, incompressible fluid between two very long parallel plates with spacing b. Here's the spacing b. Far from...
Consider steady laminar flow. What is laminar flow? Laminar flow occurs when a fluid, liquid or gas moves in smooth parallel layers with minimal to no mixing between them. Consider steady laminar flow of a viscous incompressible fluid between two very long parallel plates spacingly. Far from the channel entrance, the z and y components of fluid velocity are zero. The upper wall is stationary. The flow is driven by the motion of the lower wall at constant velocity, u. By a pressure gradient in the x direction.
The channel entrance, the z and y components of the fluid velocity are zero. So you're told that v and w are zero. The upper wall here is fixed, it's stationary. But the flow is driven by the motion of the lower wall. So this is like Couette flow here. We have a lower wall here moving at velocity u, and by a pressure gradient in the x direction, so dp dx here. So we have both motion of the lower wall and a pressure gradient. The effects of gravity can be neglected, starting from the full incompressible continuity and momentum equations, derive an expression for the...
By the way, I'll just like to credit this person. You can check out his YouTube channel as well. Fluid Matters.
The fluid velocity, u of y here. And I've made a little sketch of what you would expect. And I'll point out that this is a combination of Couette flow, where you have a flow driven solely by motion of a wall, and Poisson flow, which is flow driven by a pressure gradient. These are two solutions we did in lecture, so it's a matter of combining those things. A couple of slides from chapter 4, just to refresh your memory. This is not part of the solution, but remember in chapter 4, we derived the continuity equation. This is the compressible continuity equation, but this is an incompressible flow. You're told that the flow is incompressible, so the density is a constant, so we want to use this equation. Oh yeah, I want to remind you to put this on your personal equation sheet. You'll need both of those equations potentially on the final exam. You also want to look at the momentum, of course. That's how you get the velocity profile. So this is another slide from the chapter 4 presentation. This is the x, y, and z momentum equations. In this case, we have flow in the x direction, so we want to use the x momentum equation. Again, make sure you have these equations on your personal equation sheet. And so the x momentum equation, these are the acceleration terms, pressure gradient term, the viscous term, and the gravity term. So that was just a little bit of a refresher. We'll go back to the problem here. Before we get to the math, it's good to have a look at the problem and think about it. A few things to note from the problem statement. You're told that there's no flow in the y or z directions. So let's just remember, in the x direction,
Okay, so given that I don't have any prior knowledge of these signs right here, I'm just going to ask ChatGPT what what all the unusual signs, the unique signs here entail. So you have the F and V with the arrows, right arrows right there. It's a vector, okay. Quantity with magnitude in direction, we already know that. But here is where we get kind of a little bit confused. Okay, so here's the unit vectors. They're derived as I, j, k. They point in the x, y, z. But why are they I, j, k if they're just practically x, y, z? Okay, that's where I get a little bit confused. So we have the partial derivative. You've already encountered this earlier. We also have the derivative or the gradient. Is this a gradient operator or hold on, just a del? It's just called del. I thought it was some kind of. I thought it was gradient operator. Spatial operator completes spatial rates of change. Think of it as the derivative operator in space. So basically just It's basically just for, it's like you're using derivatives on spaces, like water, like literal space, or anything that involves a rate of change in movement. So you have your divergence. Measures how much a vector field spreads out or converges at a point. Output is a scalar. So you have del and a little dot right here, which means divergence. Measures how much a vector field spreads out or converges at a point. The output is a scalar. Then we have the curl, measures how much a vector field rotates or swirls around a point. It's a vector. Okay, so I'm just going to continue this study session later on in the day because we can't really cover all of this in just a matter of a few minutes. But at least we had some foundational knowledge that could bring us closer to eventually solving this student guide, the Navier-Stokes equation. You still have to learn the basic principles and the basic science that circulate through these topics. Okay. So that'll be all for this study session for now, but later on I'll still make a continuation of this. So thank you.